Okay, this is the lecture video for MAC 1105 College Algebra. We're in section 5.2a where we're looking at logarithmic functions, specifically evaluating logarithmic functions. Just a brief discussion regarding logarithmic functions with respect to exponential functions, which were in the previous section. They are inverses of each other. So when you're studying inverses of each other, one of the questions that comes up quite often is what is the difference between the domain of each of these functions and the range of each of these functions? If you recall from previous sections, when you have two functions that are inverses, their domain and their range switch responsibilities. The x's switch with the y's. In the simplest sense of explaining it, the x's and the y's switch responsibilities. You're going to be asked to go a little bit more in depth and to have a little deeper discussion. So the domain of the original function, which would be the exponential functions, is the range of the inverse, which would be the logarithmic function. So their domain and their range switch. The domain of the original becomes the range of the inverse. And we'll just call the f function, those would be the exponential functions that we studied in section 5.1. And these inverses that we are now talking about would be the logarithmic functions that we're talking about in section 5.2. Okay, so whatever the domain is of an exponential function, it's the range of the logarithmic function. Okay, same is true about the range. The range of the original, which would be the exponential function, is the domain of the inverse, which would be the logarithmic function. So domain and range switch responsibilities, and there's usually a conversation about that. If you graph both of these graphs, they would create mirror images on either side of a line called y equal to x. And we won't be getting into that in this section, but it may come up in the discussion in part B. Okay, so the main thing that we want to learn in this section is how to evaluate logarithmic functions. And so a lot of that has to do with learning how to rewrite from exponential form to logarithmic form and vice versa. Specifically going from log form to back into exponential form, because that's the one you're going to be more familiar with and able to evaluate from that particular form. Okay, so we're going to start with that, how to go back and forth between exponential form and logarithmic form. Okay, so let's say that you have, doesn't matter which one you want to start with, I've presented both of them to you here. But if you do have something that's in log form, it's going to have a base, but so does an exponential expression. It also has a base. So this little base that you see hanging off of either the word log, which is a common log, or when you see it on an expression that stands for natural log, ln. Either of those log expressions can be in the front. It'll have a base. That base gets pushed up when you're going to try and put it in exponential form, and then the argument of the log, the expression that's right out in front of the word log, that's the argument, that switches place with the item that's all by itself on the equals on the other side of the equal sign. So these two will switch sides, which is what these arrows are about, when you go to put it in this form. So push up that base, there it is right there, and then notice that on the side where the base was, there was an x, now there's a y. And that's because the y and the x shift sides when you're going to go from log form to exponential form. Okay, the y comes over and is now on the side where the base is, and the x goes over and is now by itself. So we're going to practice that over and over again. I want you to take note of some things that are going to be important when you're working and evaluating logarithmic functions. First of all, this argument has to always be greater than 0. It has to be positive because otherwise the log is not defined. In fact, if you try to enter anything in your calculator where you're entering log of a negative number, it's going to quit on you. It is undefined for a negative argument. So that argument, that expression right out in front of the word log or ln has to be positive. And the base has to be positive. This base down here also has to be positive, and it can't be 1. So those are some stipulations on any kind of logarithmic function that stop it from being undefined. And this is equivalent to this, and it is much of what we're going to practice in the next examples. Okay, all of these, in these examples, you see that they are in exponential form. There's no mention of logarithmic here, so that's what you're going to be doing. So that's the instructions say. You're changing from exponential form into logarithmic form. So this is the base right now. This is the exponent. This is the item by itself. So when you go into log form, just write the word log. And you might want to put the equal sign just so you can establish a left side from a right side. That'll help you, provide a little clarity for you. This base that you see right here will drop down and be the base of the log. And then at that point, once you decide what to do with the base, you're either going to push it up if you're going from log form into exponential form, or you're going to drop it down when you're starting off in exponential form. So that base is still the base, but it's the base on the log. At that point, you only have the 2 and the x left over, and they're going to switch sides. If the 2 was over here with the base, it'll now be on the other side all by itself, and the x will come over and be on the same side as the base. So the x is going to go right here. Let me give myself a little bit more room. So the x will be right here, and then on the other side of the equal sign, all by itself, will be the 2. These remaining 2 items, after you decide what to do with the base, the remaining 2 items just switch sides. X comes over here, the 2 comes over there, and it is now in its equivalent logarithmic form. Okay, let's do that again. Okay, find the base right now in exponential form. This is the base. I think everybody in this class is typically great at knowing what the base is when they're looking at an exponential function. Okay, you're still going to use that same base, but you're going to drop it down and hang it right off of the log expression. It is lower than what this is, on a lower level than this. At that point, all you have is the 3 and the 8 left over, and they need to switch the sides they're on. So putting an equal sign would be a good way of establishing a left and a right. This 8 will come over to the side where the base is, and the 3 will go over and take its place, be all by itself now instead of with the base. So the 8 comes right here and is on the same level as log. You can also rewrite these with natural log. So like this, you could rewrite them like this. You could go ln, you can put your equal sign so that you have a left and a right, and then you can start putting things where they belong. Again, identify the base here. This is the base. Therefore, you're going to hang it right off of the log, and then you're going to switch sides for these 2 things that remain. So instead of the -3 being on the side where the base is, it'll now be on the opposite side by itself. These 2 things switch sides. And let me give myself more room here, or else it's going to go right into my log. And this 1/25 will go right here. Okay, one more here. Okay, so you can go log Put your equal sign in this particular case. Now, maybe you don't know what the base is, so that's why we need to know how to write things in their equivalent form, so that if we're thinking about identifying the base to get this problem started, we need to identify the base. So this is the same thing as 8 to the 1/3. And now it is very clear which one's the base. Maybe when it's under the radical, it's not so clear, but that's why we need to know how to rewrite radicals. So that base will still be the base. And then the things that are left over, the 1/3 and the 2. The 1/3 was on the side with the base. It will no longer be on the same side as the base. Over there by itself, and then the 2 comes over here. So this is the equivalent logarithmic form. Again, these logs can be written using log or ln. When you definitely want to use the ln is when there's any kind, and you'll have to see what the preference is of the homework software that you're using. Sometimes they prefer the ln, so you can take a look at that as you use the examples, as you complete the examples. Okay, here are some more examples, just rewriting, going back the other way. Now it's in logarithmic form, and you want to go back to its equivalent exponential form. Very useful, because that's mostly what you're going to be doing when you solve logarithmic equations. So going back to its exponential form, its equivalent exponential form. So again, concentrate on the base, because it is still going to be the base when you put it in exponential form. There's your base. This item that is with the hanging base, get it on the other side and bring the 3 over here. Again, they will switch sides. So the 3 will now come over here to where the base is, but it's the base acting as the base of the exponential expression. Put that equal sign, so you got a left and a right, and the x will come over here and take the place of the 3, this time being the item that's all by itself rather than the 3. So again, just concentrate on that base. If it's the hanging base while in logarithmic form, just push it up and let it be the base of the exponential expression. So here's the base, here's the exponent. We went and grabbed this number that was all by itself, brought it over here to where the base is, acting as the exponent, and then the x went over and took its place. So those remaining 2 items swap sides, just like when you're going from exponential form into logarithmic form. Okay, same thing here. If there's no base mentioned on ln, it's automatically an e. If there's no base mentioned on log, then it's automatically a 10. Okay, just to know, so you don't think you're missing something, because we are trying to concentrate on the base just to get us centered and focused. So we're going to push that base up. Let it be the base of your exponential expression. We're going to go to the side where the item is that's by itself, grab it and allow it to be the exponent on our base. And then the 5 goes over and takes its place. So again, these 2 things switch sides. Just push up that base, bring the y over here, let it be the exponent, 5 goes over and takes its place. Same thing for this one. Okay, push up that base, go grab the item that's by itself, it comes over here to act as the exponent, and this goes over and stands in its place. And you can see that when you're rewriting things from logarithmic form into exponential form, it sometimes produces a statement that can be easily solved, like this one. If they did ask you to solve for x, you would just press in 7 to the 3rd. Or it produces a statement that you can check as being true. 10 to the -3rd actually is 1 over 1,000. I mean, it's how we rewrite negative exponents. You know, this is the same thing as 1 over 10 to the third, and 1 over 10 to the third is 1,000. So sometimes it produces, you know, when you rearrange things based on logarithmic exponential equivalency definition, it produces things that are easy to check. So we'll be using this skill a lot when we go to solve logarithmic equations. Okay, one more there. Writing the equivalent exponential form of this logarithmic expression. Take that base, push it up, still allowing it to be the base. Go grab the item that's by itself on the other side, bring it over here to where the base is, and let it be the exponent. And this jumps over and takes its place. And that's cute. That's true. This is another true statement. 125 to a power of 1/3. Fractional powers really mean it's a radical. There's a radical wrapped around this 125. The kind of radical, if you wanted to rewrite it, is cube root, suggested by that denominator. So that actually is true. Cube root of 125 is 5. If you hear snoring in the background, please excuse it. It's my puppy in the corner, and I can't get him to move. But I think you can still hear me pretty clearly. Okay, moving on. Just a couple of properties that I threw in here for simplifying logarithms, and that is what's called the inverse property, and that is when the argument, that's the value right out in front of the log, matches the base when these can be proven by using the properties for rewriting equivalent exponential functions, the equivalent exponential function of the logarithmic function. If you wanted to prove that this was true, you could do it that way using those properties on the previous page. But when the argument matches the base, this entire thing is equivalent to whatever is in this power position, which if there's no power, you know it's a 1, and that's why that's equal to 1. But if you had something like this, this would also be true, which is in the next one, I guess, so I can just wait to say what I was going to say until we get to the next property. Okay, also, anytime you're taking the log of 1, and you can put that in your calculator, you can also prove this by using the rewrite properties from the previous page. Log of 1 is equal to 0, and that's for any base. Of course, with the stipulations that the base has to be positive. And here they rewrite it for you so that you can see why that's true. Okay, then there's these inverse properties, which you could even look at that one as the inverse property. And this just says that if the argument matches the base, if this argument matches this base, then whatever is in the exponential position is what the value of this whole thing is equal to. And that's used quite a bit. But you could also look at this property right here as the inverse property. Argument matches the base, therefore this whole thing is equal to whatever is in this power position. That's exactly what they're stating right here. So that's another inverse property of logarithms, another property of logarithms. This one, I don't know how well you can see it. It's a little bit small. But if you have a base here, and on that base you have an exponent that is actually a log expression, then if this base on the log, playing the role of the exponent, matches this base, it is equivalent to the argument of that exponent, that logarithmic exponent. Okay, so as we go to evaluate each of these logarithmic expressions, we're going to be doing so without a calculator. So right now you can state that this is equal to some unknown value, and you can go into your properties for rewriting from a logarithmic expression into an exponential expression in order to evaluate these values. You could also use the inverse properties to get the values of these. Right now, I'm going to do them, I'm just going to show you that they can be done both ways. Okay, so how about if you went like this? One of the things that we have had several examples for in this section is how do you go from logarithmic form into exponential form? You take the base, you push it up, you go grab the item that's by itself and it becomes the exponent, and then this swings over and takes its place. So this comes over here. It comes over and acts as the exponent on this base that you just pushed up, and the 125 goes and takes its place. So what happens is you end up with an exponential equation that's equivalent to this logarithmic equation, and you can just look at it, and by observation you can tell what the answer for x is. What power would have to be, what power would you have to raise 5 to in order to get 125? It would have to be 3. You can also do this problem like this, using those inverse properties. So the first way I did it was to rewrite the log expression in equivalent exponential form. And then I analyzed the resulting exponential equation and just asked myself by observation, what power would that have to be? Because it's the solution. If you're going to use the inverse properties, which I just introduced at the top of this page, then you have to rewrite this so that the argument matches the base. So you had a 125 as your argument. That's this number right out here. If you write that as 5 to the third, because that's what 125 is, with that hanging base of 5, you have this fitting the inverse property. And that is when the argument matches the base, they take each other out, taking the log with it, and whatever's in this power position is what that whole thing is equivalent to. In both cases, you get a 3. Okay, and if you want to do, some of the problems like that, you can evaluate them using that property. So like, for instance, right now you have this as the base, same thing as the argument, and how many of these do you have? If you want to put a power on here, is power 1. So when this matches this, they take each other out by the inverse property, taking the log with it, and this entire thing, its value is equivalent to whatever is in that power position. That's equal to 1. Okay, and now this next one. Okay, now it's up to you how you want to do this. You can rewrite it as an equation. We can also use the inverse property. I'm going to go equation style first. So if you were going to do this one as an equation, you would go 25, take the base. I'm rewriting it in exponential form. Take this base that's on the logarithmic expression, push it up, still allowing it to be the base. The x will come over and be its exponent, and the 1/5 will come over here, so that you're creating an equation where you're going to solve. So you can just ask yourself, what power could I possibly raise this 25 to that would result in a 1/5? Now, if you took the square root, the only way you're going to go from a bigger number to a smaller number like this is if you take some kind of root. So if you took the square root, which is really written as a power of 1/2, going 25, because you want to know what the power is. Whenever you use powers that are fractions, that really means you're doing a radical. So fractional powers suggest that you're taking like either a square root or a cube root. Like, in other words, if you say that this x is 1/2, you're taking a square root. If you say that this x is 1/3, you're taking a cube root. Now, if you were going to take a square root, it would just be like this. 25 to the 1/2 really means this, which would be 5. However, you want this 5 to come out in the denominator, and to make things come out in the denominator, the power has to be negative. So 25 to the negative 1/2 would be 1 over square root of 25. This 1/2 still means square root. The negative just means it's happening in the denominator, and that would make you get 1/5. So 25 to what power would give you 1 over 5? This would be your answer. Okay. And you can just give the value. Okay, then moving on to part D. In part D, just the way this is written, there's really no work. It fits right into the mold of the inverse property. You have the base. Otherwise, I would rewrite it and try to think about the solution, but it fits perfectly the inverse property. This base matches the argument, and since this matches this, these take each other out, take the log with it, and whatever's in the exponential position is what it simplifies to. So you've evaluated that. This one right here, this also is a perfect fit for one of the properties that you've been given. Again, you can solve these as equations just using the properties of how to rewrite an expression from log form to exponential form. See if you do it right here. I mean, it clearly says right up here that the log of 1, any base, is 0. You could also do it like this. You could say, what value is this equal to? This is equal to some unknown value. With you having to show your work because the directions say do not use a calculator. If you rewrote this in exponential form, if you rewrite this in exponential form, then it would just be take this base, push it up, still use it as a base. This x will come over and serve as the exponent, and the 1 will jump over and take its place. I mean the 5, sorry. The 5 will jump over and take its place. No, what did I just do? 5, you push that up, that becomes the base. X comes over and is the exponent, and the 1. The 1 goes over there and takes its place. Excuse me. Okay, and so when you look at that, you ask yourself, what power could you possibly have there? What power can you raise anything to such that it'll be a 1? And that answer is 0. Okay, but it also says that up there in the properties that have been given in this section, that the log of 1 any base is equal to 0, but that's because you can do this. You can rewrite it to actually solve it as an equation where you'll get the same answer. So a lot of these problems can be done 2 ways. That's my point. That you can either rewrite them and or you can use these properties that were given in this section. Okay, so this one, let's say you want to rewrite it as and use the inverse property that you were taught in this section. It would be like this. Log of, this is 8 to the 1/3. Okay, just practicing with you how to rewrite from radical form into fractional exponent form. Taking the cube root of something is the same thing as raising that number to a power of 1/3. This had a base of 2. Now the inverse property still doesn't apply because you don't have the argument matching the base. But if you continue to rewrite it, if you want to go with this particular method, you could go 2 to the 3rd, there's your 8, raised to a power of 1/3. This argument still doesn't match this base, but almost there. You could leave that as the base. This would be 3 raised to a power of 1/3, or in other words, 3 times 1/3, which is just 1. 3 times 1/3 is 1. So that power multiplied by that power, in other words, raising a power to a power, you get a 1. Now the argument matches the base, and by the inverse property, these go out with the log, and this entire value is equal to 1, what the exponent is. Okay, moving on to this next one, we have, this is in perfect inverse form. The argument matches the base. And when the argument matches the base, right away you can go into canceling, take the log with it, and whatever's in the exponential position is what this is equal to. So by the inverse property, this is equal to 4. I also used the inverse property in part F, but I had to do quite a bit of rewriting to get me there, to get it to where the argument matched the base. Okay, first thing I had to know was how to rewrite cube root in power form. Cube root's the same thing as 1/3. I then still saw that the 8 didn't match that, so I wrote it using the same base, 2 to the 3rd. Then I mingled this power with this power to get a 1, and then I finally got there. So quite a few steps happened, but I was all, from the very beginning, I had the intention to use the inverse property. Likewise here. No base on your log means the base is 10. That little base is 10. So, want to use the inverse property here? You could go log base 10, and whatever the base is, you want to rewrite this argument using that base, using that same base. So you have to say, what is the power that a 10 could possibly be raised to end up with something that has 1, 2, 3, 4, 5, 6 zeros on it? That would have to be to a power of 6. However, this number that you have with all these zeros in it, isn't it happening in the denominator? And just so you can see this, see, there it is. 1, 2, 3, 4, 5, 6. Same number that you're seeing in the denominator. But when the number is occurring in the denominator, we keep going over the fact that things that are occurring in the denominator can be expressed when you're putting them in exponential form using a negative exponent. So if this would have just been a number that started with a 1 and had 6 zeros on it, then it would have just been 10 to the 6. But because it's happening in the bottom, it's 10 to the negative 6, that number that starts with 1 and has 6 zeros on it. But in that, once you get it in this form, it's in perfect inverse form. Argument matches the base, takes the log with it, and whatever's in the exponential position is the value of this entire expression. Okay, moving to part I. Okay, again, in this problem, again, we're going to have to know how to rewrite things in exponential form, because only then can the inverse property apply. Okay, there's no little hanging base here, therefore it's a 10. And that being said, I want to rewrite this argument using base 10. So when you're taking the 8th root of 10 to the first power, 10 to the first power is the same thing as 10. That's the same thing. 8th root of 10 to the first power is the same thing as 10 to the 1/8. The power that's attached to this radicand stays attached to the radicand. The index becomes the denominator of the exponent. But now you're in perfect inverse form and you can evaluate the function. Apply that inverse property, those match, take the word log with it, and this entire value is equal to whatever that exponent is, so 1/8. Okay, moving to part J. On part J, I don't know about this pencil. Okay, so when ln doesn't show a base, it is said to be an E. Get a pencil that works. Okay, so if we're going to apply the inverse property here, it's ln. What you're seeing right here as an argument, 1 over e to the fifth, is the same thing as e to the negative fifth. If you don't want to have it in fraction form, but rather in base exponent form, which is what you wanted, and if you're going to try to apply the inverse property. So there's your argument in base exponent form. The base on the log was e, and now this is a perfect fit for the inverse property, where the argument matches the base of the log, and because they match, that inverse property applies, taking the log with it, regardless of whether it's log or ln. And what's in the exponential position is what it simplifies to. Likewise for this one. The base is 10 here. This, let's get you to recognize that. This is log base 10, and this 0.01, this is 1/100th. This 1 that you see right here is in the hundredths place. How many hundredths is it? Well, the number that you're seeing there. This is 1/100th. Okay, how do we continue to make it be a perfect fit for the inverse? Rewrite this number in the argument using this kind of base. Right now, that's not what it looks like. So it's log base 10, and 1 over 100, which is just the equivalent of 0.01, is the same thing as 10 to the negative 2. This is the same thing as 100 happening in the denominator. But by writing it like this argument matches the base. They're out, taking the log with it, and the value of this entire expression is what's in the exponential position. Okay, now this, you're not going to rewrite this so that the argument matches the base. It's not going to happen here. So flip back to the other method that was emphasized here, that you could either apply the inverse properties, the properties that you learned on the previous page, or you can just say that this is equal. I did plenty of them this way. This is equal to some unknown value, and then use the other major skill taught in this section, that if you want to go from a log equation to an exponential, to its equivalent exponential equation, that was what the whole first and second page were about. That's where you would just go push up the base, go grab the item by itself and bring it over here to where you've pushed up the base. It becomes the exponent of your exponential equation, and this goes over and takes its place. So the x comes over here to the side where you're pushing up the base. That x comes over to this side but becomes its exponent, and the 1 goes over and takes its place. Now look at that and solve it. So by observation, what power can you raise any number to so that it would be equal to 1? Power of 0. Anything raised to the 0 power is 1. Okay, 12.501 raised to a power of 0 is 1. So by observation, that x would have to be 0. And if that's what x is here, that means that the value of this entire thing is 0. You can do it either way. Last problem. Either way, you can either say that this is equal to some unknown value, and then you could rewrite it in its equivalent exponential form by pushing up this base, bringing this x over to where the base is that you are now pushing up, and let the 81 swing over in its place. And you could just look at this and observe, hey, what must that power be? In order for this to be true, it would have to be 2. Okay, that's going into your equivalent logarithmic form. Or maybe this is easier for you. Sometimes one is easier than the other depending on what kind of numbers they've thrown you. You could have also made the inverse property apply very easily here. Hanging base of 9, but then the argument can also be rewritten using a base of 9, because that's the key if you're going to use the inverse property, that you can rewrite the argument with the same kind of base that you see hanging off the log. And if you can get argument to match the base, you've analyzed it. It's equal to the value of this logarithmic expression is equal to 2, just like you got an answer of 2 when you did it the other way. Okay, that completes the examples from section 5.2a, where we were evaluating logarithmic functions, learning how to go back and forth between logarithmic form and exponential form.